to learn about how to balance redox equations. First, we'll start with oxidation states, and then we'll use oxidation states to determine how to balance redox reactions. First, some simple rules. Elements by themselves, remember, are zero. So these are things that exist in the elemental form. Hydrogen in the form of H2 by itself, oxygen in the form of O2 by itself, those are zero. Otherwise, hydrogen is 1 plus and oxygen is 2 minus. Those are the usual charges. Sodium, when it's by itself, which you rarely see, but when it's by itself, it's zero. But if it's any compound, it would be 1 plus, and so on. Ions by themselves, if you have an ion that's just by itself with a charge, then the oxidation state is simply the charge of the ion. Zinc is 2 plus, zinc 2 plus is 2 plus, chloride ion is 1 minus. Now, the rest of the time we'll talk about how to do it for the other ions. So let's try the permanganate ion. To get the permanganate ion, let's break it down by the elements. The manganese, the oxygen, and the total. There's one manganese there, whose charge we don't know. There's 4 oxygens whose charge we do know. We'll assume that they're the usual charge, 2 minus. Oxygen in a compound is usually 2 minus. Now the total is 1 minus. The total is 1 minus because of what's written up there in the upper right-hand corner. Now the oxygens together make a total of 8 minus. So what does the manganese have to be to make the total 1 minus? That's right, 7 plus. So the manganese is 7 plus. The 7 plus and the 8 minus make a total of 1 minus. All right, let's try another one. Well, a little more complicated here. C3H6O, this is some kind of organic molecule. Propanol, I think it is. We'll break it down by elements just as before. Put the elements in. Remember, the carbons, we don't know the oxidation state. There are 3 of them. But the hydrogens we do. There's 6 of them. We'll assume that they're each 1 plus. And there's 1 oxygen whose total is 2 minus. Gather up the charges. 6 plus for the hydrogen and 2 minus for the oxygen. But what about the total charge? Well, the total charge is not written, so we assume it's 0. So now what does the carbon have to be to make the total 0? Don't worry about each carbon, just the 3 carbons together. What would they need to be? 4 minus. Now we're not going to try to break that down carbon by carbon. There's no need to do that. But the carbons, when they're 4 minus, together with the 6 hydrogens and the 1 oxygen, that totals out to 0. Now that we know this, we can use this to balance a redox equation. Let's try one. So this is the C3H6O with the MnO4 minus, and this is going to go to MnO2 and carbon dioxide. It's a redox equation, but it may not be obvious at first which is actually being reduced and which is being oxidized. But there's a series of steps that we'll use, and we'll go through it step by step. Balance atoms that change. That generally means the atoms other than hydrogen and oxygen. Determine the oxidation states of the atoms that do change. And if the atoms are together, keep the oxidation states together. There's no need to break it down by atom. Find out how many electrons are gained and lost by each of the atoms or groups of atoms. Determine the least common multiple and multiply as needed to make the least common multiple. Look at the total charge, not the oxidation state, but the total charge that's actually written, and add H plus or OH minus to balance the total charge. Now, whether you add H plus or OH minus depends on whether you're balancing in acid or in base, and it will tell you which it is. In this case, we're balancing in base, so we'll add OH minus. Then you look at the oxygens and balance them with waters as needed. And then the final step is just a checking step. we never actually balance the hydrogens. They should balance themselves. Check to be sure they do. If they don't, go back and see where we messed up. All right, so let's start with the first one. Balance atoms that change. Well, the manganese changes oxidation state. It looks like it does. But there's one in each side, so we're all right there. The other one that's not hydrogen or oxygen is carbon. And carbon is not balanced, so we'll need to balance it by adding a 3 to the carbons of the carbon dioxide on the right. Now we determine the oxidation states. The oxidation state of the carbon, as we saw before, was 4-. These are the 3 carbons together, was 4-. And as we did before, the manganese was 7+. Now on the right side, if you look, you'll see that the manganese goes to 4+, because each oxygen is 2- and the total is 0. So manganese has to be 4+ to balance all that. And as for the carbon dioxide, the carbon is also 4+, but there's 3 in them. Remember, we keep the 3 carbons together, so that's why I put 12+ there. So those are the oxidation states. The manganese are in blue and the carbon in black. Now we'll look how many electrons were gained and how many were lost. Looking at the numbers here, it looks like the manganese gained 3 electrons, went from 7+ down to 4+. Remember, when you become less positive or more negative, you're gaining electrons. So manganese gained 3 electrons. And the 3 carbons, together, they went from 4- all the way up to 12+. So the 3 carbons together lost 16 electrons. I know that's not a whole number of electrons per carbon. That's why we keep the carbons together. Okay, now we're going to look at the least common multiple. The least common multiple of 3 and 16. Well, they're relatively prime, so we'll have to multiply them. The least common multiple is 48. Now that we know the least common multiple, we can take out the charges because we don't need them anymore. The number of electrons for manganese is 3. To bring it up to 48, we have to multiply by 16. So multiply manganese by 16. And then the 3 carbons, those are 16 electrons. We multiply by 3 to get 48. So first the manganese, we multiply the manganese by 16. And then the carbons, we multiply by 3. So there's a 3 in front of the C3H6O. And then that 3 that was in front of the CO2, because we had to multiply by 3 again, gives up to 9. I'll do that again so you can see the carbons. Here it was before we multiplied. Here it was after we multiplied. Multiply everything through by 3. Okay, now that we've done our multiplication, our next step is to balance the total charge. And we're balancing in base, so we're going to balance it with hydroxides. Well, let's look at the total charge on each side here. The total charge on the left side is 16-, and we know this because the C3H6O has a charge understood to be 0. 3 times 0 is still 0. And the permanganate has a 1- explicitly written there, the minus sign there. That's multiplied by 16, so that gives you 16-. Notice we're not worrying about oxidation states. We're just multiplying coefficients times the charge that's actually written. If there's no charge written, it's 0. So on the left side is 16-. Now before I tell you, look on the right side, and what is the total charge going to be on the right side of the equation? Yep, there's no charge written. It's 0. Now we're going to have to balance. So we have to balance those charges, and we're balancing with hydroxides. Hydroxides are negatively charged, so we're going to take whichever side is more positive, in this case the right side with the 0, and add hydroxides to bring it down till it matches the left side to make it 16-. Now had we been doing this in acid, if we had been doing this in acid, then we'd have to add H+ to the left side to bring it up to 0. But here we're knocking down the charge because we're adding hydroxide because it tells us to do it in base. So how many hydroxides do we need to bring it down? 16. Now both sides have a total explicit charge of 16 minus. Okay, the next is to balance the oxygens. We're balancing the oxygens with waters, but first we have to see how many oxygens we already have. And if you can take a look, as you see here, there's oxygens all over the place, and this is going to be a lot of math here to multiply it out, but it shouldn't be too bad. Let's just try it and see. Yes, the numbers are big. You might want to pause this video first and count it up yourself. Okay, let's see what you got. On the left side, there's 3 plus 6 plus 64. That's 16 times 4 is 64. Right over here, 16 times 4. And that gives you 67 oxygens on the left side. On the right side, 32 from the 16 MnO2s, plus 18 from the 9 CO2s, plus 16 from the 16 OH minuses. That all adds up to 66. So 67 on the left side, 66 on the right side. To balance that, all we have to do is add 1 water to the right side to bring both up to 67. So we'll do that. There we are. Now, believe it or not, this is balanced. Let's just check to be sure, because we've checked for everything except the hydrogen. If the hydrogen is balanced, we can be pretty confident the rest of it's balanced. And so we checked for the balanced hydrogens. Turns out the hydrogens are not too high in number. There's 18 on either side. The 3C6H6Os gives you 18 hydrogens. And on the right side, you got the 16 hydroxides plus the 2 from the water to give you up to 18. Okay, reaction's balanced. Now let's try one more. This is the aluminum air battery. You actually take a piece of aluminum foil. All you need is aluminum foil, activated charcoal that you can get from any aquarium supply store, salt, vinegar, and a paper towel. And it would be a good idea to have a spatula, like a kitchen spatula, made out of stainless steel or something other than aluminum. You put all that together, you actually get a battery that can give you about half an amp of current. And so you can actually use that to run stuff. And this that battery works by the following reaction in acid. Aluminum plus oxygen from the air to give you aluminum ions. So the aluminum on the left side is in the form of the aluminum foil, and on the right side is in the form of the ions. We're going to balance first the atoms that change. Now, this one's a little bit tricky because oxygen this time is one of the atoms that does change. Normally we've been balancing atoms other than hydrogen and oxygen. This time oxygen actually is doing something. But on the left side, oxygen is 0. That's an unusual charge. The usual charge for oxygen is 2 minus. But that's in the form of water. We'll assume that the oxygens become waters. So we don't have to worry about the oxygens on the right side because we're going to balance stuff with water later anyway. So we'll leave the oxygen alone, and the aluminum is already balanced. The first step is done. Now we determine oxidation states. The aluminum, as you can see, goes from 0 to 3 plus. The oxygen starts at 0, and on the right side is in the form of water. And in water, oxygen's 2 minus. But there's 2 of them, so that's actually 4 minus. Here they are written here. Notice that the 4 minus is not written underneath anything because we're going to add water later. But we know that those 2 oxygen atoms on the left side from the O2 gas, they become some form of oxygen in the form of 2 minus. Remember, there's 2 of them, so it's actually 4 minus. Now, how many were gained or lost? Aluminum went from 0 to 3 plus, it lost 3 electrons. Oxygen went from 0 to 4 minus, so the 2 oxygens together, remember we keep stuff together, gained 4 electrons. Least common multiple is 12. Alright, now that we determined what the electrons are and the least common multiple, we don't need the charges anymore. We're going to multiply now to get the least common multiple. What do we multiply the aluminum by? Multiply the aluminum by 4. What do we multiply the oxygen by? Multiply the oxygen by 3. Notice we still haven't balanced the oxygens on the right side. because we'll take care of that later. Now we're going to look at the total charges and balances needed. What's the total charge on the left side? Keep in mind, if there's no charge explicitly written, it's 0. So sure enough, the total charge on the left side is 0, and the total charge on the right side, 12 plus. Multiply the charge by the coefficient, 4 plus, 12 plus. Remember, if there was something else on the right side that was charged, like let's say there were 4 chlorides or something, then that would bring it down to 8 plus, right? Because the 4 times 1 minus is 4 minus plus the 12 plus gives you to 8 plus. So just add everything together, add the charges together on each side. All right, so the charges are not balanced, of course, so we have to add H plus or OH minus. We're balancing an acid this time, so we're going to add H plus. We're going to add H plus to whichever side is more negative to bring it up. So we're going to add H pluses to the left side to bring it up. The difference is 12, so we need to add 12 H pluses. Now you examine the oxygens. You see there's 6 on the left side and none of them on the right side. Balance them with water. There's your 6 waters. And then finally you check for the balanced hydrogens, but you can see that there's 12 on both sides, so that's fine. And that's how you balance the reaction. Thank you for listening, everybody.